keynote talk. And Steve did his PhD from Cambridge. And after that, he took up a 2 years postdoctoral position at Hawaii. And after that, he also joined as a postdoctoral fellow in Space Telescope. And finally, he also joined U of T for a brief period of time before going to Cardiff. And he will be talking about cosmography with Herschel.
Okay, thank you very much. I can almost apologize for the title. I've only just discovered the word cosmography, which I rather like, because cosmology is about measuring the basic parameters of the universe, and that's always seemed to be a little bit narrow. Cosmography, as I understand it, is not only measuring the basic parameters of the universe, but measuring the general properties of the things inside the universe. So it's kind of everything. If you think cosmology is everything, cosmography is even more of everything. It's the universe and everything within it. And it's a kind of a nice way to unify some of the themes in this talk, which are basically going to be about research with Herschel. So, and I should acknowledge that an awful lot of this work, and most of this work, is being done as part of huge international collaborative teams, in particular the Herschel ATLAS team, the Herschel Reference Survey team, and the Helder team. When this first talk about the Helder observations, and this is not obviously cosmography, because it's observations of just one galaxy, so it's not the universe at large, it's observations of one galaxy. But the reason it's a kind of cosmographic survey in some ways is because we only know a relatively small amount about spiral galaxies. I mean, the spiral galaxy we know most about is our own, because we sit inside it and have an amazing resolution. Virtually all other spiral galaxies are too far away to learn much about. But the crucial second spiral galaxy we can learn things about is the Andromeda galaxy in the local group, simply because we have superb resolution and sensitivity when we observe it. And in particular, Herschel observations of M31 have the same resolution, have enough resolution that you can start to see individual giant molecular clouds in the galaxy, which means you can try and understand dust and star formation on a physical scale similar to the scale we can see in our own galaxy. And the physics of star formation is undoubtedly linked to the physics of GMCs. And so to really study it, you need to be able to resolve galaxies on the scale of GMCs. Okay, so these are a few observations, a few pictures of M31. As I said, it's got superb observational data. There's a lovely atomic hydrogen map by Robert Braun, published in 2009. There's a CO map that was obtained after 3 years observations on the Ion telescope. And it's been observed at Spitzer.
Sorry,
oh, sorry, I didn't know slide here. Oh, yes. Much better when we do that. Anyway, so M31 is the other big spiral in the local group, but it's interesting as a contrast to the Milky Way for a number of reasons. Firstly, it has an exceptionally high ratio of atomic to molecular gas. And secondly, there's more evidence from the structures in the gas of the stars from recent interactions in the midst of the Milky Way. So in the case of M31, there's a huge star-forming ring, and you don't see a similar structure in the Milky Way. So the next thing I'm going to show is a kind of pretty slideshow, and it's showing the Andromeda galaxy seen by 3 European space missions, Planck, XMM Newton in X-rays, and Herschel. And the European Space Agency made this just after we did our observations of M31 in Christmas 2010. So it's a pretty show, but at least it does show the importance of complementary observations. So here's the optical picture of the Milky Way, and there you can see Andromeda appearing. We're now shading over to Planck in microwaves. We're now going to focus in on Andromeda. So Planck obviously has pretty low resolution, although it can't really resolve it. We're now going to move into the optical. And you see the big bulge of old stars in the middle. We're now going to fade into our Herschel 250 micron map. And the bulge of old stars now vanishes because the dust and the emission from Herschel traces the dust is mostly in star-forming regions. And here's our 250 micron Herschel image. And we're now going to fade into the XMM Newton X-ray observation that basically picks up very old objects, so objects in the bulge. Okay, so on to the detail of the science. Well, we observed M31 in 5 bands between 100 and 500 microns. And our analysis was sort of fairly simple. We convolved all images to the same resolution as our lowest resolution image, which is at 500 microns. We re-gridded to pixels, to big pixels that are completely independent, which gave us 4,000 independent pixels. So if anyone used to doing observations of galaxies, the idea of having 4,000 independent pixels is really quite stunning. And then we fit single temperature modified black bodies to the 110 to 500 micron data, allowing the temperature and beta, which is the slope of the emissivity, to vary. And we found that virtually all cases we could fit the data with this single temperature model. So the data gave no reason to look for a more complicated model. And we got similar results if we omitted the 110 micron observations. Now, anyone that does this kind of work knows there tends to be a degeneracy when you're fitting a modified black body. The errors in the temperature and beta are correlated, and this shows the Monte Carlo simulation of the effect of the correlation and the errors. But the results I'm going to show do not appear, for a variety of reasons, to be affected by this degeneracy. So the first thing at the top is if you look at the temperature plots, and this is temperature against radius, and you can see that the main feature you see in the temperature plot is the temperature is roughly constant at around 17 Kelvin all the way into the centre, and then about 3 kiloparsecs from the centre it starts to increase. And you explain the increase rather nicely because that's the region of the stellar bulge. And if you plot down here we've got the temperature against the flux at 3.6 microns in the stellar bulge, and you can see this very strong correlation. So the evidence is that this increase in temperature in the centre is almost certainly due to the heating of dust grains by the old stars in the bulge. In the rest of the galaxy, we assume that the temperature of dust is a lot colder. It is generally heated by the interstellar radiation field, which will be a mixture of old stars and the young OB stars formed in the star-forming regions. Now, the really interesting result we got, which we can't explain, but it appears to be a genuine result, is that beta, which is the emissivity index of the dust, appears to vary with radius. And so this is typically thought to be around 2. And in M31 you can see in the star-forming ring around here, it's slightly below 2. As you go to smaller radii, it increases, and about 3 kiloparsecs it starts to decrease. Now, beta tells you something about the properties of the dust, but we don't really understand what's causing this variation. It's not seen, it wasn't seen in the Milky Way by Planck, and it's not seen in some other galaxies that we've observed in the Virgo cluster, but it does appear to be seen in M31. My speculation is that the star-forming ring in M31, which you'll see in a moment, is kind of gradually moving out through the galaxy, and this is actually had the result of its processing the dust grains. Now we've also tried to map the star formation rate of this galaxy, and we use a fairly standard technique, which is to use the UV radiation measured by the GALAX telescope to measure the unobscured star formation, and the 24 micron emission observed by the Spitzer Observatory to measure the obscured star formation. Now, in M31 you have to do something subtly slightly different because it's a galaxy in which the star formation rate is actually quite low. And so some of the UV radiation is undoubtedly coming from old stars, and some of the 24 micron emission is undoubtedly coming from dust that is not being heated by the young stars, the OV stars, but it's being heated by the general stellar radiation field. And we investigated this by plotting, by using the 3.6 micron emission measured by Spitzer to kind of measure the intensity of the old stellar population. What we have here is unfortunately these haven't come out terribly well. This is the 24 micron emission in each pixel against the 3.6 micron emission in each pixel. And the different colours correspond to points at a different distance from the centre of the galaxy. So the red points are points within the central 20% within about 3 kiloparsecs from the centre, and then the other points are pixels which are further out. And you can see that for the further out pixels, there's little correlation between the 24 and the 3.6 micron, but for the points in the central region, there's a very strong correlation. And so what we're finding here undoubtedly is that in the central region, the 24 micron emission is definitely dominated by dust that is being heated by the old stars in the bulge. And we fit a line to this relationship, and we then use this relationship of the 3.6 micron image to correct the UV emission for every other pixel in M31. And here we do the same thing for the UV. Ignore that line here. We use this relationship to correct all the UV emission from old stars. So the point is, what we do is we use the UV and 24 micron emission to measure the unobscured and the obscured star formation, but we use the Spitzer 3.6 micron emission to make a correction for the effect of the old or the general stellar population on UV and the 24 micron. And when you do that, you get this diagram here. This is the star formation rate. And you can see the star formation rate is dominated by this ring, this about 10 kiloparsecs, and there's a small inner ring around there. And the global star formation rate is about 0.3 solar masses per year, so it's much lower than in many other galaxies, and is rather lower than in the Milky Way. So anyway, I said one of the points of observing M31, apart from the fact it's there, is to contrast the Milky Way and Andromeda. And we actually get quite different results from the Planck observations of the Milky Way. So there's a whole slew of papers by the Planck team on observing dust in the Milky Way. And one difference between the Milky Way and Andromeda is the Planck team don't find any evidence for radial variation in beta, the emissivity index. And they also don't find any evidence for the dust optical depth for hydrogen atom varies in radius. So this is actually from Planck team. So this is essentially, it's the dust optical depth, so you can think of this as the column density of dust, divided by the column density of hydrogen atoms, measured from H1 and CO, plotted against distance, and you can see there's no variation. Now this is actually a little bit surprising, because you might expect there to be a radial variation because of the metallicity gradient in the Milky Way, but the Planck team don't see that. And they do also find a difference in the temperature profile from the one we get from Andromeda, because this shows the temperature profile for the Milky Way, and you can see the temperature is steadily dropping with radius, and you don't see that from Andromeda. You see the temperature dropping in the bulge, but is then roughly constant as you go further out of the disk.
Right. So that's the optical depth.
No, this is the optical depth in the submillimeter.
Yeah,
So it's kind of you can think of this, it's equivalent to the column density of dust.
But you said beta, is that?
I should have actually said, because I realise there's people might not know this. The modified black body is the Planck function times mu to the beta. Okay, so beta is the emissivity index, and beta is typically between 1 to 2. So sorry, say your question again.
Well, so I guess I'm just wondering exactly how beta translates, variation of beta translates into variation in that quantity.
If beta is varying, then if beta is a constant, then then this thing is not necessarily a constant. Because
I guess it would be constant if the metallicity was constant.
Well, you might expect it to be. You might expect it to be. Yeah, if metallicity, there's no gradient in metallicity, you might expect, not necessarily, but it'd be reasonable to expect that the dust to hydrogen atom ratio should stay constant.
I guess I'm wondering, you said it was the most surprising that it's somehow the case that metallicity, you take into account the metallicity variation, somehow the emissivity is compensating for that.
That's right. So if you assume that if you've got a gas or a particular metallicity and you assume that a constant fraction of the metals in dust grains, then you would expect the optical depth of H to track the metallicity, which it appears to do in Andromeda, but it doesn't appear to do all the Planck observations suggest it doesn't do that. So now the other interesting result of Planck team got is they found evidence that a large amount of the gas in the Milky Way is dark gas. And now for 30, 40 years, the ways that astronomers have measured gas in the interstellar medium is to use the 21 centimeter line to measure the atomic hydrogen and the CO10 line to trace the molecular gas. Now it's always, the 21 centimeter line is a pretty unambiguous way of looking at the atomic phase of the interstellar medium. CO is not so unambiguous because CO is an optically thick line. It's also a trace molecule, so each CO molecule traces 10,000 hydrogen molecules. And the translation between CO and the bulk of the molecular gas that you're not directly observing is kind of controversial. But it's always been assumed that you are actually detecting all the molecular gas and the atomic gas with these two traces. But the Planck team found evidence that that's not actually necessarily the case. So what they did here is, this is the dust optical depth again. So you can think of this as the dust column density. And here we have the column density in gas obtained from the 21 centimeter line and from the CO line. And if the CO and the 21 centimeter are tracing the gas, and if the dust grains are also tracing the gas, you would expect a nice relationship between the two. And you get a kind of a nice slope with a gradient of 1 where the column density of gas is low, and also where the column density of gas is high, but you get this weird kink in the middle. And the interpretation that the Planck team gave to this kink is that in this kind of region here, there's plenty of molecular gas, and you're seeing it, or you're tracing it with the dust grains in the molecular gas, but the CO line is no longer tracing the gas. And the reason they argued for this is that around molecular clouds, you may have plenty of molecular hydrogen, but the interstellar radiation field might make you disassociating the CO molecules. So they concluded that as much as 50% of the molecular gas is not actually detected in the CO line, but instead it's basically something you can't observe unless you trace it in some other way, and in this case they're tracing it with the actual dust. Now this also suggests, or this suggests to me when I read the paper, and it suggests to many other people, that maybe actually dust grains are actually a better way of tracing gas than CO. Because in both cases, in the case of dust and CO, you're actually using particles that are relatively rare to trace the molecular gas, and there's obviously issues to do with metallicity. If the metallicity is varying, then in either case you have to make a correction for that. But the dust grains may well be a more robust way, or something that is found in every phase of the interstellar medium, and may be robust to changes in the interstellar radiation field in the CO. So anyway, so this kind of diagram suggests that maybe dust is better than CO.
What about higher order CO transitions?
Higher order CO transitions have complications because then you have temperature effects. So you have to then, because I think they're less optically thick, which is better, but you have to start modeling the temperature. The other thing you can use in this kind of region is probably the C2 line with 150 microns, which is tracing ionized carbon. And there's also the possibility of C1 line. So there are other possible ways of doing it, but they're all quite observationally difficult. Now the reason that dust is would be quite nice as a way of tracing gas is that it's also a practical thing to observe, because in the case of Herschel, as I've showed, we had dust observations of hundreds of thousands of galaxies, and if we could use those observations to measure the interstellar medium of these objects, we'd be in a very good situation. Even with telescopes like ALMA, it's going to be difficult to measure the CO in very large numbers of high-redshift galaxies. And this plot is an attempt that I made to try and see whether you could use dust to measure the mass of the ISM in galaxies. What I've done here is I've taken 10 galaxies in the Virgo cluster and estimated the mass of the interstellar medium in those galaxies from the dust, and also from the CO and the H1. And you can see that actually they do follow each other pretty well. So I think dust has got a potential for measure as a way of actually measuring the interstellar medium in lots of galaxies. Anyway, to go back to dark gas, we did the same thing as the Planck team did for the Milky Way for M31, and this is essentially the optical depth in the dust again, or the column density of dust, and this is the column density of gas estimated from the H1 and 21 centimeters, that's the H1 and the CO. And remember, in the case of the Milky Way, there was a kind of kink around here. We don't see any evidence for that. However, it doesn't mean the Planck team are necessarily wrong. It doesn't even mean that Andromeda is necessarily different from the Milky Way. It could be that the Planck observations have better physical resolution because we're within the Milky Way than our observations of M31, even though they're pretty good resolution. And each of our pixels is integrating along the line of sight through the galaxy and averaging over a range of environments. So it's possible this method, which is used by the Planck team, is not sensitive enough to actually see the dark gas. But we do have one advantage over Planck, because we can actually see Andromeda from the outside. And so what we can do is we can plot an image of the ISM as estimated from the dust after divided by the ISM estimated from the CO and H1. And this is the plot you get. I've corrected for a radial metallicity gradient, but you can see even after we've done that, there appears to be some variation in the ratio of the ISM from dust over the ISM from CO and H1 as you go around the galaxy. So it's possible the places where it's red here, there is actually dark gas, but it's also possible that the dust properties are actually changing in those regions. So I'm ending on this section on a note of ambiguity, because we've kind of taken our Herschel observations as far as they can go. We found possible evidence for dark gas, but it's not actually clear whether it is or not. The only way we can really go beyond this is to start mapping M31 in spectral lines like the C2 line that might show up dark gas, even if the dark gas is not in the CO. Okay, I'll go over this very quickly. As I said at the beginning, the reason that we want to observe M31, the reason M31 is a potentially interesting object to look at, is we can start to separate out the individual GMCs and try and understand how the star formation rate in each GMC depends on perhaps its environment within M31 and other things. And this just shows the first attempt to do this. We've taken our images of the dust in M31 and we've run a source finder to find the individual peaks. So each of these points represents a potential giant molecular cloud. And there's about 700 of these peaks in M31. compared with previous observations that used interferometers of more distant galaxies, typically find around 35 GMCs. So this is kind of work in progress. I think I'll flip over this because I don't think this is particularly useful, and then go on to the more statistical part of this talk, which is with the Herschel ATLAS. So this is a genuine cosmographic survey because we can not only try and understand things about the cosmological parameters, but we can also try and understand what's actually out there in the universe, both within the galaxy and actually outside the galaxy. So this is the widest area survey of Herschel. It covers 550 square degrees, which is 1/80th of the sky. We cover 5 bands with the 2 cameras on Herschel, Pax and Spire, and the 5 bands of 110, 160, 250, 350, 500 microns. And we expect to detect around 300,000 galaxies. Possibly rather more than that, but definitely 300,000 galaxies. And our primary aim was actually to provide the kind of link that Sloan and the 2DF Galaxy Redshift Survey did in the optical, but in the far infrared submillimeter. So for those of you that are interested in galaxies, you will know that the big things that 2DF and Sloan did was they measured redshifts for hundreds of thousands of nearby galaxies, which allowed you to kind of map out the cosmic web, but also investigate how the properties of galaxies depend on things like environment. The missing link in the statistical 2DF and SDSS surveys was that they could do things like look at the optical star formation and look at the star formation that was not obscured by dust, but they couldn't look at the star formation that was obscured by dust, and they couldn't actually measure the ISM of the galaxies. In principle, Herschel could do that. So our initial motivation was to sort of, we weren't really interested in the high redshift universe, we were interested in the low redshift universe. We wanted to do the first submillimeter survey of a very large number of galaxies in the nearby universe. But it turned out that actually Atlas has a very large number of things you can do with it. So one is our local universe survey. We detect about 300,000 galaxies out to a redshift of 3. We detect roughly 50 to 70,000 out to a redshift of 0.3. So a very large number of objects in the nearby universe. As we are the only big Herschel survey covering such a large area of the sky, there's obvious synergies with the Planck-Wall Sky survey, because we can take Planck point sources and then see what these Planck point sources are actually made of. It turns out one of the most interesting things you can do with ATLAS is to find gravitational lenses, and the gravitational lenses can be used for all kinds of things, including measuring cosmological parameters and studying the dark matter halos that we see out in the universe. And then there's obvious things like looking at AGN, large-scale structure. And it turns out you can even do things in the galaxy because we're looking, we try to avoid the galaxy by looking away from the Milky Way. So we're looking at high galactic latitudes. But the advantage of that is that anything we do detect within our galaxy, in our images, is very close. And so it turns out we can look at debris disks, and we've also found some possible very low mass star-forming clouds. This just shows the regions of sky we're looking at. We've been looking at. The image behind is the IRAS 100 micron map of the sky, and so you can see where the dust within our galaxy is. We try to avoid this, so we tended to try to put our fields in dark regions on these images, but we also wanted to give maximum overlap with existing and planned surveys for the wavelengths. In particular, all the spectroscopic surveys such as SDSS, the 2DF Galaxy Redshift Survey, and the recent Gamma Redshift Survey. So it was a compromise between lack of galactic dust and existence of a survey. So in most cases, we're in regions where there's little dust in our galaxy, but in the case of these fields here, these are in fields where there's actually quite a bit of galactic dust, but they're also fields that were surveyed by the Gamma Redshift Survey, so they're particularly interesting to decide to do with those. Now, Herschel is going to finish operations in next March or April, and our survey is basically complete in terms of the observations and mostly complete in terms of the data reduction. In the first few months after Herschel was launched, we obtained data in a small field, a science demonstration field, and we've now publicly released this data, which is Herschel data for 7,000 sources, and data on the optical and infrared counterparts of those sources, and that's on the website hatlas.org. So that data has already been released. Our phase 1 data, which is the data on the fields along the celestial equator, is essentially complete, and our data release is planned for December 2012, although it may actually be early next year. And then the really big maps, which are the maps of the South Atlantic Pole and the North Atlantic Pole, the data's been taken and preliminary maps have been made, and the final data release will be planned for the end of 2013. This just shows our NGP map, which is kind of hard to show because essentially it's 70,000, probably 80,000 sources, and it's in the North Atlantic Pole. It's away from nearby galaxies, so it's very hard to display it and do it justice. And there's this one nearby galaxy within it. This big image here is about 1/16 of the entire field. You still can't see much. If you then focus in on the little green box here, this shows a false colour image of the green box made by combining our free long wavelength images. So red shows something that's either very cold or very high redshift, and blue shows something that's kind of warm or low redshift. In most cases, what we're seeing is something that represents redshift. So the red sources with high redshift and the blue sources with low redshift. Perhaps you can see rather better by going to our science demonstration field, which comprised 3% of the final area. This is the whole field. Again, it's quite hard to see things. If we focus it on a little bit, you can start to see the individual objects. So most of these things are high redshift galaxies. The tenuous stuff you see across is dust in our own galaxy, so it's dust at high galactic latitude, kind of wispy silicate material. And then this one object, right at the bottom, is we coined with the customary lack of creativity in galactic astronomers. We call this the blob. And this is a very low mass star. It's either a protostar, very low mass protostar, or it's a very low mass pre-stellar core. It's really a very interesting object. And it turns out this was the first field we found this one galactic object in it. We've now looked over all the other images in the whole 550 square degrees, and there was nothing comparable to this in all the fields. So it's a mysterious object. We still don't quite understand its nature. So let me just give you a few results from the science demonstration phase. So the first thing you do when you have one of these images is you run a source extraction software on the image, and that produces a catalogue. And in the case of the science demonstration field, we had a catalogue of 6,600 sources. The next thing you do is you try and find the counterparts, the optical or infrared counterparts to those sources. And this is where it gets a bit difficult because the Herschel beam is quite large, which means the positional accuracy of Herschel is not very great. And also the optical data we have in slow digital sprite survey images, which are not very big. But anyway, we use those to find reliable counterparts to about 1/3 of the Herschel sources. But it's important to point out that the statistical analysis shows that probably about 60% of the Herschel sources are counterparts on the slow images, but the positional accuracy of Herschel is just not quite good enough to actually make those reliable counterparts. So in principle, the slow images are deep enough to detect about 60% of the sources, but we just can't tell what the counterparts are. But anyway, taking the 1/3 of reliable counterparts, this shows the redshift distribution, and you can see that there are a large number of very low redshift sources, and so you can start to do interesting things at fairly low redshifts that you couldn't before our survey. And one of the things you can do is to do what all extragalactic astronomers like to do, which is to plot luminosity functions. And this shows the galaxy luminosity functions, which is the space density of galaxies as a function of luminosity, plotted against luminosity in 5 redshift bins. So the black lines are at redshift less than 0.1, the red points are at redshift between 0.1 and 0.2, the green points are at redshift between 0.2 and 0.3, etc. And the point is, when everyone's seen cosmic evolution before, we all know about cosmic evolution, but the nice thing about our results is we've shown cosmic evolution at a very low redshift. And that's useful because you can then try and understand, observationally, it's easier to try and figure out what is causing that evolution. And so the classic phrase that people use is the evolution caused by nature something intrinsic to the galaxies, or is it caused by the environment of the galaxies? So is the environment of the galaxies changing in some way, which is then causing the galaxies to be more luminous and causing cosmic evolution, or is it something intrinsic to the galaxies? So we tried to do this by quantifying the environmental density of each Herschel galaxy. I won't we use a thing called the D5 statistic is the main thing I've used, which is the surface density of galaxies within 1,000 kilometers per second of the Herschel galaxy, and closer on the sky than the 5th closest galaxy. Essentially, it's something that quantifies how rich the environment is. And we've estimated the D5 statistic for 2 redshift bins, redshift 0 to 0.09, and redshift 0.09 to 0.18. Now, the first thing is that there is a spectacular lack of correlation between the D5 criterion, so the environmental density of the galaxy, and the Herschel luminosity. So the Herschel luminosity, which is probably telling you something about either star formation rate or how much material is in the galaxy, has no very little correlation with the surface density of galaxies around it. Let me show you another one. Let me show you this. And this plot here shows the luminosity function in 2 redshift bins for galaxies with very high values of D5. So this is for galaxies in very dense environments. And I tried to see whether you can see stronger evolution in galaxies with very dense environments and in low density environments, and you don't see any effect at all. So basically, the bottom line is you see no environmental effects at all. But we do see a possible evidence of something that's intrinsic to the galaxies, because what we've done for each galaxy is we've kind of used the Herschel observations to estimate the mass of dust in each galaxy. And this is plotting the thing called the dust mass function, which is the surface density of galaxies, space density of galaxies as a function of dust mass. And again, I've divided things into redshift bins. And what you see that in the same way the luminosity was increasing, or the luminosity function was increasing in the redshift, it's a rather messier diagram, but you see evidence of the dust mass function increasing in the redshift. So the bottom line is there's evidence that as you go back in time, galaxies contain more mass, more gas. And so there's no evidence that the evolution is caused by environment, but there is evidence that as you go back in redshift, the galaxies contain more material. And so our observations so far are strong evidence for nature rather than nurture. Now I'm just going to go over to Planck follow-up. This is just one slide really. There's 28 sources from the Planck early release catalogue in our phase 1 fields. So we can figure out what these sources are made of. 2 of the Planck bands are common to 2 of our bands. So 350 microns and 500 microns are the 2 highest frequency Planck bands, and they're our 2 longest wavelength bands. So we can kind of make a direct comparison between the Planck images and our images. And of the 28 Planck point sources, we find that 16 are basically just dust in our own galaxy, Sirius emission. There are 10 low redshift galaxies, and then there's one very high redshift lens system. And I just showed some high resolution observations of that one lens system. I somehow managed to reverse this slide. Now, probably the most exciting first result we got from the survey was that we showed that there's a way you can use Herschel observations to find gravitational lenses. And this was a method that had been suggested by Mattia Negrello, who was a postdoc at the time, working in Italy, and he was one of the original ATLAS team. And he'd argued from his models that actually, if you observe the bright sources at 500 microns, you find that most of those were gravitational lenses. And I never really believed him, even though it was one of the things that put in our original proposal. But it turns out he was dead right. And this is shown very nicely by the next couple of slides. So this is our science demonstration field. And in that field, there were 11 sources with 500 micron fluxes brighter than 100 millijanskas. One of these is the blob, the galactic object. There was one blazar, which is an active galaxy. It's very easy to spot because they're bright radio sources. So you can just take a radio survey and just show that you've got a blazar there. And then you have some other objects, and these are 4 of the other objects. And these are the Herschel images. But if you look on the Sloan images, you see these are just nearby galaxies. So there were 4 very nearby galaxies of our 11 sources. So we have 11 sources. One was a galactic object, one was a blazar, and there were 4 nearby galaxies. And all of these things were easy to spot, no problems at all. And of course, that left 5 sources. So here are the 5 sources that were left. And first thing we did is looked at the Sloan images of each of these sources, and you find that at the position of each source, there is a galaxy. And the galaxies are at kind of moderate redshift. So redshift between 0.2 and 0.8. So one possibility, of course, is that what we're seeing here are the Herschel galaxies, the galaxies that are emitting the Herschel radiation. But there was immediately one thing that suggested that wasn't the case. Because the crucial thing about Herschel is you can use the Herschel colours to estimate the redshifts of the sources. So what I've got here is the ratio of 350 over 500 micron flux versus 250 over 350 micron flux. And what we've done is taken two low redshift galaxies, ARC-220 and M82, and tried to see how those colours of ARC-220 and M82 would change as you move the things out in redshift. And you start out at a, get this right, you start out at very low redshift up here, and then as the galaxy moves up in redshift, the colours should get flatter. And when we looked at the Herschel colours of these 5 sources, we plotted them here, and the estimated redshifts from the Herschel colours were much, much higher than the redshifts of the galaxies visible in the Sloan images. Now, a few years ago, it would have been impossible to get much further than this, because if you've got a high redshift, possibly high redshift Herschel source and a low redshift galaxy possibly in front of it, how do you measure the redshift of the high redshift Herschel source? And you can't do it using optical techniques. But recently, a number of groups have measured and have developed spectrometers capable of observing CO lines, molecular lines at high redshift. And we immediately got on the telephone to various people around the world who've got these devices. And I think our first observations were on March 9th, 2010, only a couple of months after our first observations with Herschel. And our first observations were with the Z spectrometer on the Caltech submarine observatory. and line's not very obvious here, there's a line, the line is here, but we've got a redshift of 3.04, much higher than the redshift of the Sloan galaxy, and a few days later we confirm that with observations with the Green Bank telescope and the Z spectrometer. Getting the same redshift. And in fact, of the these first five objects, these are the optical redshifts, and these are the redshifts measured by the CO line. So you really have got five cases where there's a high redshift source, a measured redshift, and there's a low redshift galaxy directly between you and the high redshift source. And the low redshift galaxy is clearly gravitationally lensing the high redshift source. And this essentially gave us, as long as we stuck to the bright Herschel sources, 100% success rate for finding gravitational lenses. And Mattia wrote a paper was published in Science in 2010 describing this. Now, it turns out it's a little bit complicated to go. This method works really well for the bright Herschel sources, but as soon as you go to the fainter Herschel sources, it's more difficult. Because you start finding large numbers of unlensed sources. And we immediately realized that this method was potentially a way of finding very large numbers of lens systems, hundreds to thousands of lens systems. But it's only recently we figured out observationally how to pick those sources out. So anyway, what can you do with lenses? Well, the obvious thing that a lot of people immediately started doing is making lensing models. And this shows some results from a paper by Shane Bussman, which is just being appeared on AstroPH. And what he's done is used images of the Herschel sources made with the Smithsonian millimeter array. These are things shown in red. And the redshifts of the sources and the redshifts of the lenses to try and estimate things like the masses of the lenses, the masses of and to reconstruct the source emission. Which you can do surprisingly well. So you can measure massive lenses with a precision of about 4%. So what else can you do? Well, what we've been doing over the last couple of years is trying to measure as many redshifts of Herschel sources with all these CO spectrometers. And we've so far got 22 sources with redshifts between 1 and 4.2. And in all cases, there's actually evidence that these things are actually being lensed. What I've plotted here is a figure from taken by Andrew Harris, in which the blue points are our Herschel sources, and he's plotted the CO luminosity versus the CO line width. And the red points show a comparison sample of unlensed high redshift sub-millimeter sources. And you can see our Herschel points, for a given line width, they have much higher CO luminosities, and the obvious explanation of this is that you're seeing gravitational lensing, and just by measuring how far these points are off this line, you can work out the magnification. So we've got magnifications between 20 and 3. Now, the CO spectrometers can only take you a certain way, because you can obviously can't measure redshifts from 300,000 sources. So what we've been doing is taking these redshifts and then calibrating a method for using the spire photometry, so the long wavelength Herschel photometry, to estimate the redshifts. So what my student Elizabeth Pearson has done here, she's taken the 20 or so galaxies with redshifts, she's then worked out the rest frame, or the rest frame wavelengths corresponding to the Herschel emission, and then she's tried to fit a template to the entire sample, producing a kind of universal sample template that you can then use to estimate the redshifts for the Herschel sources. I can answer, if anyone's interested in the details, I can tell them later. But anyway, we've got a technique now for estimating the redshifts for the Herschel sources, even when you don't have CO spectroscopy. And when you do this, you find redshift distributions like this. So the two crucial things. The first thing is that it's a bimodal distribution of every band. So you find a very large low redshift peak, then you find a second high redshift peak, and the relative size of the peaks depends on the wavelength. And the redshift of the higher redshift peak kind of increases as it goes along the wavelength. But the crucial thing is the fact there are two peaks. And that suggests that what we're seeing with Herschel are two populations of galaxies. And Andy Alappa, who's in our team, has shown that you can explain the properties of the high redshift peak rather nicely by a model in which all the high redshift sources are actually ellipticals being formed in single bursts of star formation. So I covered back in the envelope model for this to explain these distributions is the high redshift peak comes from forming galaxies that are being formed as a result of relatively sudden collapses of gas. And then the low redshift peak corresponds to more normal galaxies with star formation rates that are much more rapid as well.
What's been done in terms of cross-correlating the high redshift sources with APM?
There has been no work. That's an interesting point. We have done work on taking the Herschel images and then taking samples of high redshift quasars and then looking for how many quasars are detected. But when people were doing that, they didn't have access to these estimated redshifts. So we've now got estimated redshifts for everything. So we can do that. Actually, that's an interesting thing that we could do. So suddenly having these estimated redshifts has been throwing up lots of interesting projects. Another one that we want to do is look at the correlation function in different redshift slices. And so there's kind of lots of fun things you can start to do. This just shows that it is kind of plausible that these high redshift sources are actually proto-ellipticals. What I've done here is, rather than plotting redshift and luminosity, I've turned redshift into cosmic time, and I've used Kennicott's relation to take a bolometric luminosity and turn it into a star formation rate. So you can see, as you go back in time, the Herschel sources start to have very high star formation rates. So you go into star formation rates of up to 1,000 solar masses a year, and the red lines show the star formation rates necessary to make an elliptical of particular stellar mass in the lesser of 1 gig a year and 10% of look back time. So if you're interested in a low redshift elliptical that's got a stellar mass of 10 to the 11.5, you can see that anything above that line, any Herschel sources above that line, could make all the stars, make enough stars to make a low redshift elliptical of that size in about 10% of that time. So it's quite plausible these things are actually proto-ellipticals. However, the big thing that's holding us up is many of these things are undoubtedly lens systems. So our estimates of star formation rates are going to be wrong because of the effects of gravitational lensing. And the big thing we've been struggling with over the last 2 years is how to take this very large sample, very large survey, and figure out what's lensed and what's not lensed. So we've been carrying out all kinds of observational things and theoretical modelling to try and understand how we can either get rid of the lensing or find the sources that aren't lensed, or on the other hand, find the sources that are lensed and do interesting cosmological or cosmographic things with them. And one thing we found, postdoc in Cardiff, Joanne Short, has done this. She's been doing large numbers of simulations, and she's shown that our slow images are not actually deep enough. Because for a particular, given lens profile and a particular assumption about the masses, how the space density of dark matter halos varies in redshift, she's shown what the most probable lens redshift and lens halo mass should be. And this is shown by these things here. And you can see that it's kind of peaking around the redshift of about 0.6 and a halo mass of around about 10 to the 13.5. But to link this to observations, the solid line shows the limiting halo mass that should be found on the slow images, which are the ones we've mostly been using. And you can see the slow images will miss about 60% of the actual lenses. If you go to the near infrared, to the Viking K-band survey, you do much better, and you then start to be able to potentially find all the lenses. Now we think we started to be able to do, we think that I say we, but critical guidance made most of the work, is Joachim Gonzalez Nuevo. We think we can now use the K-band data to really find the lenses. So what we do is we estimate the redshifts of the Herschel sources from the Herschel colours, and this shows a particular set of sources that have near-infrared galaxies very close to the position of the Herschel source, and then this shows the estimated redshifts of the near-infrared galaxy. So these two pictures are for a sample of sources with high estimated redshifts from Herschel, but which nevertheless have near-infrared images very close to the Herschel positions on the Viking K-band images. And you can see that the redshift distributions are very different, which suggests that in these cases you really are seeing lots of lens systems, because the redshift of the thing you see on the near-infrared is a much lower redshift than the thing that you find in the redshift of the Herschel source. And so we think by using this near-infrared data and looking for sources, ATLAS sources with high estimated redshifts, but near-infrared counterparts, we can actually find the lens systems, or conversely, we can get rid of the lens systems. And this is potentially a great way of finding large numbers of lenses, because the distribution of lens redshifts we get, which is shown by the dark line here, extends to a much higher redshift than the redshifts of the lenses found by other lensing or attempted-to-find lenses, such as the ones based on the Sloan survey. So we've potentially got a way of finding a very, very large number of lens systems in ATLAS. And I did a rough calculation just before putting in an ALMA proposal, and we reckon there are about 10,000 of these in the full survey. So of the 300,000 sources, about 10,000 appears to be sources that are being strongly lensed. Okay, so what can you do with this? Well, people are working on gravitational lenses and wanting a technique for finding large numbers of lenses for a long time. Because there's all kinds of fun things you can do. So, for example, you can try and measure cosmological parameters, so I'll show you an example of that in a moment. You can do something like you can measure the average density profile of the dark matter halos, which are the things that are doing the lensing, and that's important because the only real ways you can do that are by lensing techniques. So, something you may not know, but probably most of you do know, all galaxy formation models usually start with an evolving population of dark matter halos. The guys that predicted how to produce an evolving population were Pessencheck back in '74, but people doing n-body simulations and other analytical work has kind of improved on that. And so every galaxy formation model starts with this evolving population of dark matter halos. But there's really been no observational way of really checking this sort of basic part of all the models. And now with a very large lensing survey, you can kind of start to do that. And then this should be a very easy thing observationally, because our Herschel sources are so bright, we can take all our lens candidates, and essentially 1 minute with ALMA will be enough to confirm whether the thing is lensable or not. And this just shows how example again from Joe Short, how you can start to constrain cosmological parameters. So in this case, she's shown the constraints given on Omega Lambda by first a sample of 5 lenses, then 100 lenses, and then 10,000 lenses. And you can start to put constraints on cosmological parameters, including measuring equation of state for dark energy, once you start to get to these very large lensing surveys. Okay, I'll stop there. But the key thing that I want to kind of emphasize is that although most of the data at the moment is still proprietary, firstly, the maps catalogues and catalogues of optical counterparts to our phase 1 data, which is actually the best data in some ways because it's along the equator and has the best spectroscopic surveys, will be released to the general community either very late this year, or more likely now early next year. So if you have ideas what you want to do with this kind of data, measuring correlation junctions or whatever, we're looking for AGN, high redshift, that will be available and you can use it. You can practice on our science demonstration data, which is available on our website, atlas.org. So the data is of similar quality, so it's only 6,000 objects, but it's still enough to get started. But the other thing I want to emphasize is that although our team contains 150 people, the number of active people in it is relatively low. And so there's an awful lot of people that signed up right at the beginning and have never done much. So we're always looking for new blood. And in particular, if you have ideas for projects or science that we're not currently doing, it's relatively easy to kind of get taken on by the team and to get access early. So, we really, European Space Agency tells us we have to be open to the community, but actually you kind of want to be open to the community anyway, in very much the same way that Sloan has got most of its science from not from keeping things within the Sloan team, but actually releasing things to the community as soon as possible. So I will be here today and tomorrow, so if you want to chat about any of this, please come and see me. But if you think of something later, just contact me by email. And if it's something you're not already doing, then it's quite likely we'll just say, yeah, come aboard and you can play with our data. Okay, thanks very much.
We'll take your questions because you already maps of other
well, one thing I should say about Herschel is that the European Space Agency basically said that any data taken in the first year had to go into the Herschel archive within 12 months, and any data taken after that had to be put in the archive after 6 months. So most of the data, including the data I'm talking about here, is already in the archive. And is often in a very usable form. So all the data taken with the Spire camera, which is the kind of workhorse camera, it's already been processed and it's just sitting in the archive. So if you're interested in, suppose you're interested in the galaxy, I don't know, M100, which is actually one of the galaxies we've observed as part of another project, you can just download the images and play with it immediately, and you don't have to ask any more permission to do so. This data, the release I'm talking about here is kind of essentially enhanced Herschel data. It's our Herschel maps processed in a slightly better way. And also the catalogue to be found by running our own source extraction software and doing all the finding all the optical counterparts. But you could basically get decent maps just now. You can just go upstairs and download stuff. It's very easy. And I started plunging other people's data because
has Herschel tell us anything about the star formation in dwarfs?
Star formation in dwarfs. It's told us
downsizing phenomena, stuff like that.
It's probably
downsizing phenomena, stuff like
that. There are target observations of dwarf galaxies which have shown that dwarf galaxies are strange objects because they have this very weird spectral energy distribution in the submillimeter that either suggests they have massive amounts of cold, very cold dust, or that the dust in dwarfs is somewhat different in some way from the dust in normal spirals, which is something that was kind of known about the dwarf before Herschel, but Herschel's basically said yes, that is still the case, and no one understands it. And there's also evidence from another very I said there's evidence of dark gas in the Milky Way, but there's evidence of even more dark gas in dwarf galaxies. So there are target observations of dwarfs. Whether, as to the whole downsizing thing for galaxies, I think most of the deep Herschel surveys are kind of consistent with that, and I don't think they necessarily added anything new. I think one place where Herschel is definitely adding something new in galaxies is there started to be very firm observation evidence of feedback, which has always been an ingredient in galaxy formation models. But the theorists tended to just sort of stick it in by hand, and there's been no observational ways to really look at it. But with Herschel and ALMA, people have been seriously starting to be able to look at see the outflow of gas. The other thing I think for people interested in star formation that I think is amazingly cool is that the people looking at low mass star formation have really made massive steps in understanding how low mass stars form, because you get these, I've got other PowerPoint presentations on here. You get these amazing Herschel pictures of different clouds. And in one cloud, there are stars forming, and another cloud, there aren't stars forming. And in both clouds, you see filaments. And the crucial thing appears to be in the density of the filaments. If the density of the filaments gets above 5 solar masses per light year, then the filaments collapse. If it's below that, they just stay as part of the interstellar weather. And the other amazingly cool thing, which is even cooler, is that wherever people look in the galaxy, the filaments always have this exactly the same look. It's always 0.15 light years. And I think that is telling you something fundamental about how gas in the interstellar medium is converted into filaments and then low mass stars. So that's really interesting. The high mass star formation is not so clear to me that Herschel's really made. It's making having an impact. It's not necessarily producing any kind of revolution. I think low mass star formation is what it's been at so far.
Okay, we can have more questions on this.